Hello community! Today I want to show you a full example of edge classification and node classification in PyTorch with a deep graph library. A full example for you to follow along. Now on my last videos I focused on node classification task and on the link prediction task. And we have videos on both topics. This is great. But what's missing is edge classification. Because not only can our nodes or vertices in our graph have feature tensors, but also our edges can have information encoded in feature tensors on the edges. So what I mean is, let's say you have two green nodes and you have an edge connecting our both vertices, our two nodes, and you have a particular information encoded on the edge. Could be a string, could be a tensor, whatever information you have, whatever is the semantic content of it. And please note, here in the first tree we have the same node type, it is green, but here we have an example with different node types, and different node types mean heterogeneous graphs. And I will show you also the code for heterogeneous graphs. Now, what is the task? Let's say in the easiest case, you have 100 edges in your graph and you want to do a classification. So which of the 100 edges belong to specific class 1 or class 2? Now, we have to predict the attributes or the features, whatever you like to call it, on the edges of our graph. And we will use a graph neural network for this. Now, to compute the prediction or the feature of an edge is more or less to express it as a parameterized function of the representation of its start node, of its end nodes of the edge, and the features on the edge itself. Now, this sounds a little bit complicated, but let's jump into the code and I will show you in detail how to code this on a full example. Today we're going to talk about edge classification of our graph, and we will do it in Deep Graph Library. So, if you have a GPU, beautiful, you install it with this command. If you have a CPU only, and this is what I will go for, because we don't want to take away the GPU on a free Colab notebook from somebody else doing research. So, beautiful, beautiful, we install NumPy, we install SciPy, we install Torch, we import DGL, everything, and we have here, we're gonna work with a GraphSAGE layer and a GraphSAGE model parsing, so we import this. Now, interestingly, to do edge classification, we need, of course, an optimal presentation of our node embeddings. Therefore, we have to invent a model for the node representational learning. So, by this, let's do node classification in Deep Graph Library just right now, because we're gonna need this model anyway for the edge classification. So here we go. So in a graph you have the node and the edges, and you have graph specific property. Those are, you can say these are features, and you have association to the edges and the node with a tensor allocation. And a feature is created via a tensor assignment, which assigns a feature to each node or each edge in the graph. Yes, 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 beautiful. Message parsing, I have a specific video on message parsing. You can build it yourself, beautiful. But we are gonna use the built-in functionality of DGL. So, first step, let's build a graph neural network model. The model should do the work for us. Beautiful. As I told you, message parsing, we're gonna use the SAGE model that's already built for us here within DGL, and as you can see here, we have here DGL SAGE layer, and we have a second layer we append to this, and we have a dropout functionality, and the feed-forward loop is straightforward. You know this with an activation function, nonlinear activation function. Here we use a ReLU function and a dropout functionality. Beautiful. This is our SAGE model we're gonna use in node classification and in edge classification. So this is an important model. Please remember this model. Beautiful. If you want to know about GraphSAGE layer in detail, where it come from, how it was invented, who invented it, there's the archive preprint inductive representational learning on large graph. Or if you just want to go for the software implementation of SAGE, You have the in feature vector, the out feature vector, the aggregation type that we're going to specify. You have a dropout function, a bias, a normalization. Beautiful. You know that by incorporating node features in the learning algorithm, we simultaneously learn the topological structure of the graph, but more important, of each node's neighborhood, as well as the distribution of node features in this specific one-hop or two-hop neighborhood. So instead of training a distinct embedding vector for each node, we have a set of aggregator functions that learn to aggregate feature information from this local neighborhood of the node in a one-hop neighborhood or in a two-hop neighborhood. We have here two layers, so we have a two-hop neighborhood for each node. Beautiful. So we need a data set, and we take a data set that is free of charge and provided for us by DGL. So we import the specific data set. The number of nodes is 3,300, the number of edges is close to 10,000, and the number of the node features are 3,703. And this is a classification task since we are focusing on node classification. So we need classes, and we have the class 0 to 5. Beautiful. Now, very short interrupt. A lot of you asked me, hey, I have a tar file or a gzip file, and I have problems unlocking the data here within DGL. Now, it is easy. You have here a utility, a data utility, where you have the download command, and you can even check for some specific sums. So what you say, hey, I have here my file path that I want where this is stored. I have here the download command with a specific URL, and please store it here. And then you can check for specific cross features. And the main part here, this is a beautiful command. Please remember this one. If you want to extract here the gzip file or whatever tar file to your specific directory, it is so easy. You just have to extract _gz. This is it, and you have the data up and running, available to you. Beautiful. Now, coming back to our graph, you know that we have now in our graph, we have the node data. Since this is a node classification task, we are looking at the node data and not at the edge data for the moment. And there we have two features. We have a feature tensor and a label tensor. Now the feature tensor is easy. Let's do this, and I just want to show you the structure, show you the data. So node features, let's have a look at this. How does this tensor look like? Oh yeah, great. So it has a shape, and you're not going to believe it, for each node, each of our 3,327 nodes, we have a feature tensor, a 3,703 dimensional feature tensor. Let's check. We have here the number of nodes, 3327, beautiful. And the number of features per node are 3,703. Great. So we have now encoded here in our node feature, the node feature tensor for each and every node in our graph. Now, yes, you can look at the first one and you can look at this last one, and they both have 3,703. So now for the node label, since this is a classification problem, we have labels 0 to 5, 6 different labels. And you're not going to believe it, we have for each of our 3,327 nodes, we have one particular label. This is stored in the node label tensor. So now you're familiar with node features and how the graph is represented internally in a DGL representation. Beautiful. Next step. We have to evaluate our model, we have to test it. We have to create test graph data for our model. How we do this? It is a non-trivial task, as I have shown you in a video, or maybe you will see this video depending where this video is broadcasted. But you know this from machine learning, training data, test data, and your evaluation data set. How we do this, we create a Boolean mask, a Boolean tensor mask. So we say for our training data, for our validation data, and our test data, we create a mask. Just to show you how this mask looks like, you're not going to believe it. It is a tensor for each of our nodes. And if you look at a complete tensor, yeah, you will see it is a Boolean tensor. False, 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 true. So we have now split up our training graph data set into the training, validation, and tests. Beautiful. It is not easy, but let's go with this. So what we have to do now, we have to find an evaluation function where we say, okay, our test data set has to go in here. So what we do, we just do an evaluation with some unseen training data. Beautiful, we split up, we have this evaluation function, and then it is time to define our training function. Now, you are not gonna believe it. We have a loss function, and this is, since it is a classification task, we have a cross entropy loss. You remember? Classes from 0 to 5. Now, with our optimizer, we go for classical Adam optimizer. You can specify your learning rate, your weight decay, everything else. I just go with the classical model. And then we enter a training loop. And let's say we have here 200. Oh yeah, maybe I should activate this too, that we have it. Yes, beautiful. And then we have 200 epochs. Maybe, yeah, let's go with 200. Yeah. That you don't think this is not live. Let's go with 180. Beautiful. So you train your model. You have then your loss function, your optimizer. You have your backpropagation. You calculate the accuracy. And we just say, okay, let's have a look at the number of epochs, the loss, and the accuracy with our validation data set. Great. So now we have the validation function, the training function. Now we just have to build the model. So beautiful. At first, if you want to take care about CPU and GPU with NVIDIA CUDA functionality, easy device CUDA, if it's available, else it's a CPU. Beautiful. We only have a CPU, so you know we're gonna be a little bit slow, but no problem at all. As I showed you, the feature we put in the feature tensor, the node labels we put in the label tensor, and we have two masks created. Beautiful. Now, for our model, it is easy. We have already defined the SAGE class where we have the input feature size, the out size. In the middle, we have with 16, we have the hidden size. And this, of course, goes either CPU or GPU. So let's do this. Great. And then here we are. We start our training and we start then finally to evaluate it on the test data set. So let's go live. Number of epochs, the loss, accuracy with the validation data set. So you see the loss goes down. Yeah, beautiful. 0.8, 0.7, 0.6. Test validation data stays at 0.7, 0.7, yeah. 0.5 of the loss goes down, beautiful. And we use the test data set. So you see for the test data set, we have an accuracy of 0.7. And for the validation data, we have 0.69. So beautiful, no overfitting, looks good for us. So this was a GraphSAGE GNN with two GraphSAGE layers end-to-end homogeneous graph node classification example. Great. You say, hey, wait, it's homogeneous? What about heterogeneous? Well, just show you in a second. If you're not interested, skip for 2 minutes. If your graph is heterogeneous, you want to gather the messages from the neighbors along all edge types. So you can use the model, and there's a specific DGL model, heterograph convolution. And this is also, of course, available in TensorFlow 2. And it allows you to perform the messing parsing on all edge types. If you have multiple edge types, you can combine it beautiful with the graph convolution model for each edge type. So you can define here the relational GCN model. Beautiful, beautiful, beautiful. You have here this specific heterograph convolution layers already defined for you. You have your feed forward, everything that you know. Then there are specific commands you are not interested. You split more or less the same. You have your feature tensor, you have your label tensor, you have your mask defined. For the forward propagation is clear. And then what you do, you have an Adam optimizer. Yes, yes, yes. And it is more or less exactly the same. If you want, as a professional example here, and I leave you the link, if you go here on DGL, And here the PyTorch examples. You can also look at this in TensorFlow, but for PyTorch, you have here the relational GCN hetero entity classifier. Beautiful. Done. Now our main topic is edge classification. You might say, hey, all this time, but yeah, we have already done half of the work. So edge classification, we want to classify edges. We just classify node, and now the other part of the graph are the edges. Beautiful. Yes, yes, yes. There is a Jupyter notebook if you want to follow along. It is with the DGL AI, and it is training minus edge. And there you find your Jupyter notebook or your Python file. Beautiful. So from the previous section I just showed you, we learned how to do node classification with a multi-layer GNN. And now you're not going to believe it, the same technique, the same method can be applied for computing the hidden representation of any node and the prediction on edges. And this is exactly what you're looking for. The classification can then be derived from the representation, from the node representation of the specific nodes. Beautiful. So here we go. For the data set, let's make a very easy data set. We have a source node, we have source nodes, and we have destination nodes. We make a symmetric graph. We build a very easy symmetric graph. And then we go exactly as I showed you. Now with the node data of our graph, we have now the feature tensor, and the feature tensor, hey, we say just create a random tensor for us, 100, 10. But now we do not have a label tensor with the nodes, with the node data, but we have now a label tensor with the edge data. So we want to predict now the edge classification. Beautiful. Yes, you can see these are just random numbers. No problem at all. This is just a demonstration. So to be fast, we have chosen this way. And then, as I showed you, we have to create here now our split in the training data set. And what we do here is we just create a training data set with a Bernoulli probability. So very easy. So we have the training mask defined. And yeah, normally you would do the validation mask and the test mask, but you know how to do this. So we just stay here with the main part. You know the other part. It is easy, the same. So let's do this, Yeah, let's have a look here now at our graph. The graph has a name. It's a little bit funny. Edge prediction graph, because this is a very specific graph. Beautiful. Now, here is the scheme. We have the graph. The number of nodes is 100. The number of edges is 1000. Exactly. This is what we set out to do. Now, the node data schemes, we have a feature. Beautiful. But with the edge data, we have a feature and we have a label, as I just showed you. And then we have now defined a training mask. This is within the graph object. And this is exactly what we have done here. So you are not surprised at all. Beautiful. Now, if you want to have a look now at the edge schema, let's do this. So what we have a look at the graph and we say, hey, show me the node features. And it is a tensor. Beautiful. Wait. Here we go. It is a feature tensor for each of our 100 nodes. Beautiful. You are amazed, but let's go on. So next is here, of course, the edge data. Now the edge data have more content, of course, because this is the way we constructed it, but let's have a look at it. At first, we have the edge feature tensor. This is a feature tensor for our edges. Then we have a label tensor where we created some random numbers. This is our label tensor. And then, as you know, we have the Boolean mask, the training data set somewhere. Where's our, here's the training data set. And we have a Boolean tensor. Beautiful. So we know exactly from all our edges which are true or false within our training data set. Great. We have the data prepared. Yes, you can look now in detail at the feature. You see this is the feature tensor. You can look in detail now at the label. You see this is the label tensor. And you can look at the Boolean training mask only. This is the Boolean training mask. Beautiful. Great. Now comes an interesting part. And here is now the main brain power. This is what you should be careful about. So assume that you compute the node representation with the model from my previous section, node classification, you only need to write another component in our ML that computes the edge prediction. And for the edge prediction, we will use a specific DGL command, apply edges. This is a beautiful command. Let me show you in detail. So if you would like to compute the specific score of an edge, if it is a classification, for edge regression, the following code computes the dot product. Again, matrix multiplication dot product of the node representation on each edge. So for one edge, you have the start node and the end node of your specific edge, and you do the dot product of the node representation. Beautiful. So here we go. We built a dot product predictor. Okay, beautiful name. So we have H contains the node representation computed from the GNN defined in our node classification section. This is exactly what I showed you just 5 minutes ago. And then we have here the command. This is the main command. Graph, apply edges, and do here a dot product between two node representation, the node U and the node V. Do the dot product and assign a score to this dot product and apply it on all edges. So let's have just this command and let's focus on this command. We start now with the inner command here, u.v. If you are working in DGL, in PyTorch, you're not familiar with this, this is easy. I'll write here this again for you, u.v. You have here the left field, the right hand field, and an output. So what it does, it's a built-in message function that computes a message on an edge by performing element-wise dots function between features of the node U and the node V if the features have the same shape. Otherwise, it first broadcasts the features to new shapes and then performs, as you know, the element-wise operation. So we start here with the feature field of the node U, the feature field of the node V, and then we have an output message field, and this is our score function that we want to assign to each and every node. So this explains what we do here, matrix multiplication of our two node representation. Great. So now we have to do this for each and every node in our graph. So as I told you, there's this beautiful command, apply edges. And the DGL library, we have apply edges, where we define a function. We say edges all, yes, edge type you can define, and this is it. What does it do, apply edges? Now, it updates the features of the specified edges, let's say all, by the provided function. So here we define a function and it is applied on all edges. This is exactly what we are looking for. The function to generate new edge features, it must either be a DGL built-in function, of course, for optimization, I suppose it is written in C, or a user-defined function. Yippee! So, what is our function here on apply edges? Easy, we have here apply edges, and our function is here u.v. So this is the matrix multiplication of the node embedding, of the node vector, of the feature vector, if you want. Great. So here we are. Now we put those two pieces together and we build our model. Now we say, given the node representation computation model from the first part, and now the second, the edge predictor model, you remember this dot product predictor, we can easily write a full graph training loop where we compute the prediction on all edges. So here we go. We built a model, a new model, and you're not going to believe it has two parts. The SAGE model, where we have from the node classification, and then here our dot product predictor. Remember, the dot product predictor is here, this beautiful thing. And SAGE, oh my goodness, SAGE, hold on, where's SAGE? Just to show you, where's my SAGE? SAGE, here, no, go back. Download, my goodness, here is my SAGE. This is my SAGE with my two SAGE layers. Beautiful. So we combine this with our dot predictor. Where are we? Feature, yes, here we go. And this is now our model. These are two parts that we need for node classification. we optimize the node embeddings, and then we do the product of the respective nodes in the new optimized vector space, feature representation space, and we get, as we defined it here, we get a score. Beautiful. So here we go. Let's do this. Again, as before, we have our features, our label, our training mask, and then we define our model. Model here, this is it. We have in features, hidden features, and out features. 1025, we have an Adam optimizer. You are familiar with this. And then we have, let's say, 500. Oh, maybe I should activate this. And then we have 500 epochs, and we do the training. And as you can see, we have only the loss. I have not defined here the I have only defined the training data set. I have not defined the validation data set, since I only have a training mask and not a validation mask and not a test mask. You can do this in whatever fashion you like. I just want to give you an idea here on a short performance. So we start here. Here we go. With a loss of 2.5. And then as you see, the loss goes down 1.111. 1 0 1 0 1. Yeah, okay. I did not need to go 500 epochs, but you are somewhere at a loss 1.0. Beautiful. So what we achieved, we have now a model. Where's our model here? This is our model that we trained. We have a trained model that is now optimized for an edge classification task. Of course, you might say, hey, this was only for the homogeneous graph structure. What about heterogeneous? Is it as easy as you showed us with node embeddings, or for node classification if you go from homogeneous node classification to a heterogeneous graph node classification task? And more or less, yes, it is. And even DGL tells you edge classification on heterogeneous graph is not very different from the homogeneous graphs I just showed you. If you wish to perform edge classification on each different edge type, you only need to compute the node representation for all node types, I've just seen, and predict on that edge type with a specific DGL heterograph apply edges. So, beautiful. And of course, our dot product predictor work on one edge type of the heterogeneous graph. You only need to specify the edge type in the apply edges method. So, as you can see, we have now a heterogeneous graph dot product predictor. And it is absolutely the same command. You just have to do this for all the different edge types. So you specify your edge type here in this definition. Great. Now, the model looks absolutely the same. You have now for the heterogeneous graph, you build your model, and you have here exactly, before we had the SAGE model, now we have a relational graph convolutional network. This was defined in the scientific literature. I will show you in a second, but it is the same. You have here a node classification model, and then you have here, based on the new optimized node embeddings, you have a hetero dot product predictor for our edges. So you see, you do this for all edge types. Beautiful. This is the model. And then you do exactly the same, the feature, the models, yes, yes, yes. And you define it, of course, for all heterograph E-types, edge types. And then you have your classical optimizer, and you just let it run for 10 epochs. And you have now, instead of a homogeneous graph, you have a heterogeneous graph. My goodness. You have your node features, and see, it is absolutely the same. Beautiful, beautiful. So, this is it. We achieved it. We have now an understanding and a complete node encoding and an edge classification here in our Jupyter Notebook. We are working here on PyTorch, and we use the DGL Deep Graph library to perform our task. And we somehow managed to perform everything. Everything was working. We worked with DGL on a free Colab notebook. I hope you had fun. I leave you here, as you can see, always the links to the understanding, to the official guide by DGL and the Jupyter notebooks or the Python files. So please download them whenever you see this specific indicator. Follow along, try yourself, get familiar with graph neural networks. It is a beautiful thing you can do. And for example, I have a video on node to vec that I did in TensorFlow. Of course, you can do the node to vec methodology. You can program it here in DGL, and it delivers amazing results. Give it a try. It is a little bit more complicated, but that would be part of another video. We just want to finish this video. So what I say thank you for watching. Thank you for listening. I hope it was clear to you. If not, you will have here the link, and I will leave in the description of this video all other links that I would recommend that you read: the papers, the books, the code segments, the Jupyter notebooks you can find. And I see you in another video.